Hello everyone, welcome to my class. Today we will hold the last lecture in module 9. Now, in module 9 till now we have covered Fresnel half period zones, vibration curve, then we studied Fresnel diffraction due to circular obstacle, then we were introduced zonal plates, and in the last lecture we talked about rectangular aperture. Today we will learn diffraction of a plane wave by a long narrow slit and transmission to the Fraunhofer region. Thereafter, we will talk about diffraction at a straight edge, then diffraction by a narrow obstacle, which would be followed by Babinet's principle, and this will conclude today's lecture and module 9 as well. Now, we will start with Fresnel diffraction by a slit. Now, slit is nothing but it is a particular case of rectangular aperture, wherein the one side of the rectangular aperture is extended till infinity. Okay. Now, this is what is written here also. We can treat Fresnel diffraction at a long slit as an extension of the rectangular aperture problem. Now, in this case the slit length or the length of one arm of the rectangular aperture is assumed to be extended till infinity. Now, in this figure the slit is extended till infinity in y direction. Now, this edge goes till minus infinity, while this edge goes to plus infinity. Okay. While in the vertical direction along z axis, the slit coordinates are z1 and z2 as depicted in this figure. Now, therefore, here the extremities of the slit in y direction, which are y1 and y2, they would be moved very far from the origin O. O is the origin of the coordinate system placed in this aperture plane. Now, since y1 and y2 are extending till infinity, therefore, u1 which is directly related to y1 and u2 which is directly related to y2, it will also extend to minus infinity and plus infinity respectively. And we know phasor therefore would be equal to square root of 2 e to the power I pi by 4. This till here we have already calculated. We know how once the u1 and u2 are minus infinity and plus infinity, then what would be the values of respective integral, and we know it would be equal to minus half and plus half. Using that, we calculate the phasor B12 would be equal to square root of 2 e to the power I pi by 4. But this is only for horizontal direction, which is along y axis. What about the integral which is in the vertical direction, the v dependent integration? Now, the integration which we are talking about is equation number 66, and which is given by this expression I p, that is irradiance at point of p is equal to I u by 4 and mod of B12 square, which is a function of u, and mod of B12 square, which is function of v. This we have already calculated in the equation 67. Now, this we have still to evaluate. The value of B12, which is function of u, is given by equation number 67. This is still to be evaluated. Now, we can see that equation number 68 is independent of u, or equation number 68 is independent of y. Yeah, because we have assumed the extremities of the slit to be at infinity, and therefore, we calculated the corresponding integration, and using that we calculated the b tilde 12 function of u. Now, the value of b tilde 12, which is function of v, it depends upon the width of the aperture in vertical direction, and that width would be v2 minus v1 or z2 minus z1. This is equivalent to z2 minus z1. Okay. That is delta z, which is directly related to delta v. Okay. Now, you see that in this figure O is the origin and P is the point of observation. Okay. At this point P, the Z1 and Z2 extremities, these lower and upper extremities of the aperture along z direction, they are symmetrically placed. This angle is equal to this angle. Okay, this theta is the same if the slit is viewed from point of observation P. Therefore, if we draw these things on Carnot spiral, then we will see that we will get a spiral like this, and then the delta V would be represented by this curve, and you can see that the length of the curve here and the length of the curve here in the third coordinate, they would be same due to the symmetry. Okay. V1 is in the negative direction, V2 is in the positive direction, and therefore, V1 would be here, V2 would be here, and the difference is V2 minus V1. Okay. Now, if we want to observe the irradiance at point P1, which is slightly downward with respect to point P, then what will happen? O would be shifted to point O1, because we know instead of calculating irradiances at different point on the screen, we move the aperture plane. Now, if you move the aperture plane, the point O will shift to new origin, which is point O1. Yeah, initially this was the slit, and then O was here, now O1 is here. Okay. For O, the point of observation was P, for O1 the point of observation is P1. Okay, these are the parallel lines here. So, sorry for my drawing, let me draw it again. Okay, this is our slit, this is point O, this is point O1. For point O, we were having point of observation P, for O1 we will have point of observation P1. Now, from P1, if you treat O1 as new origin, then this edge would be more positive and this edge would be now less negative. Yeah. For O, this is a positive edge, this is Z2 and this was Z1, but since the origin is shifted downward, Z2 would be more positive while Z1 would be less negative. Yeah, because whole reference frame got shifted down. Okay. Therefore, the coordinates of the edges would also move. Okay. The coordinates of the edges will shift upward. Okay. Initially the origin was here, and then we were seeing that it is say +2 and the lower edge was at -2, but if we shift the origin by 1 unit down, then the upper extremity which initially was at +2, it would be now +3, and the lower extremity which initially was at -2, it would be -1, because origin got shifted by 1 unit. Okay. And this also happens here in this case too, but this length Z2 minus Z1, this would not change. Okay. And similarly, the delta V, the arc length, which is equal to V2 minus V1, this will also remain fixed. Therefore, on Carnot's spiral, the delta V, which was initially symmetrically placed, it would be shifted upward in the first quadrant. Why? Because V1 is more positive and V2 is less negative. Therefore, things are shifting up in the positive direction. Yeah, and this is what is shown here. Initially, due to the symmetry, the point B1 and B2, they were symmetrically placed. This arc was equal to this arc in length when the point of observation was P, when origin one was exactly at the center of the slit. But now, if we want to calculate the irradiance at a point P1, and for P1 origin has to be shifted at point O1, in that particular case the arc is shifted, the new arc is this. Okay, this is now new arc. Okay, you can see that this point B1 is shifted to this place and B2 is shifted to this place. Okay, B1 initially was at -1 and B2 was at +1. The new position of B1 is -0.5, which is less negative, and new position of B2 is +1.5, which is more positive. Okay, and therefore, as we move down, let me show here these things in this figure. Initially the point of observation of P, if we move a bit down, the new point of observation is P1, and at P1 the arc, the curve is spiraling up, it is going up in the first quadrant. If we go more down at point P2, then at point P2 the new origin would be O2. O2 would be here in the it would be in the plane of aperture, but it would be not in the open portion of the aperture. Okay. O2 is still in the aperture plane, but it is on the closed portion now. Okay. And the point of observation for O2 is P2, which is a bit more down as compared to P1, and therefore the curve will move up. Okay. Because from O2 this edge is far, it is positive, but more positive, while the lower edge it is also positive, because origin has shifted even more down. Yeah, the origin is here and the slit is like this. Okay. Therefore, both edges of the slit are positive now. Okay. In this, it means our curve in Carnot spiral picture, it is shifted in the first quadrant. The whole curve, whole delta V now got shifted into the first quadrant. Okay. Now, let us see what happens exactly. When the origin was at the center of the slit, this line represents the irradiance B1 to tilde. Okay. Now, when we are at a point P1, this line represents the new irradiance, which is B1 to tilde, but at point P1. It means at point P1 the irradiance is decreasing, it is going down. Okay. Now, if suppose we are at a point P2, in that case when both the edges are in the positive, the whole curve is in the positive quadrant, and for this would be the new position of the curve. Okay. Where B1 is represented here and B2 is here. Okay. Now, in this case the resultant irradiance would be given by this phasor B1 to tilde. Now, you can see that this phasor is still smaller. Okay. Now, as we move below, then what will happen? The delta V or this curve, it will spiral around which point? Spiral around this point B tilde positive. Okay. And what we will see is that the irradiance, it will go through several extremum, it will go through several maxima and minima, and it will slowly decay down. Okay. Now, this is what is also written: as the point of observation moves down into the geometric shadow, the string winds about B tilde positive, and the chord goes through a series of relative extrema, and this is what I said. Yeah, sometimes it will see maximum, sometimes minimum, sometimes maximum, sometimes minimum, but it will decay down. Okay. And this is, you can see, this is the maximum length, and then the length got reduced here even smaller, and if you keep going, then you will see that sometimes you are seeing some maximum and sometimes minimum, as the chord, which is delta of length delta V, it winds around B plus tilde, okay, which is this point. Now, if delta V is very small, or if the slit is very thin, our imaginary piece of string is small. The string means this delta V, a chord which is being plotted on the Carnot spiral, and the chord decreases appreciably only when the radius of curvature of the spiral itself is small. Okay. Now, if delta V is very small, in this same picture, this, suppose this is the Carnot spiral, and let us represent the chord with blue color. Now, this is our delta V. Okay. Since slit is very thin, therefore, the length of delta V is very small, as you can see in the figure, and OS is the origin. Okay. Now, what will happen if we go down, then this chord will move up slowly, and what will you see is that this length is not decreasing appreciably. This is the position of the chord at different point of observation. If the point of observation is going down slowly, then you will see that if the chord length is very small, then the resultant phasor or resultant irradiance is not decaying as the point of observation is moved down. The length almost remains constant, therefore, irradiance would also be almost constant. And if we want to observe any reduction in the irradiance, then this Carnot spiral, it should be very small. If it is quickly winding up with a very small radius of curvature, then only we will be able to see some appreciable change in the irradiance. Okay. Similarly, if we move point of observation in the upward direction, then the chord will shift like this. Okay. With the moving positions of the point of observation, the chord will wind up around this spiral, around this point B plus tilde or B minus tilde. Okay. And this is what exactly happened with the thinner slits. Okay. You see that light diverges and a lot of light goes into the shadow region. Okay. And this is what exactly we are seeing, it decays very slowly. Okay. Now, having done this, now let us see, now this phenomena, this occurs in the vicinity of B plus and B minus. Okay. What occurs around B plus tilde and B minus tilde? The decrement of the irradiance for thin slit, yeah, because the arc length or the chord length is very small, and therefore, any reduction in the irradiance would be seen if only we are in the vicinity of B plus tilde or B minus tilde, or if the spirals are very tight and very small, if the radius of curvature is very small, then only we see a slight reduction in the irradiance. And this will happen far out into the geometric shadow, which is very much clear. Now, there will thus be light well beyond the edges of the aperture as long as the aperture is relatively small. With a small delta V, there will be a broad central maximum. In fact, if delta V is much less than 1, R naught lambda is much greater than the aperture width. Why? Because if you remember, in the definition of U and B, V R naught lambda comes in the denominator, yeah, and if R naught lambda is much greater than the aperture width, then we are effectively in the Fraunhofer regime. Okay. Therefore, we see that as we shrink the aperture width, then slowly we move from the Fresnel regime to the Fraunhofer regime, because there the Fraunhofer condition prevails. Why? Because R naught lambda is much larger, okay, and delta V is less than 1. Okay. In this particular case, we slowly move from the Fresnel region to the Fraunhofer region. Now, let us see what happens if we opens up the slit, if we widen the slit. Now, as the slit widens, what will happen? Delta V or the chord length, it will increase, it will become large. Okay. And while doing this broadening, what we do is that we fix R naught. Okay. Now, if we fix R naught and keep opening the slit, then a situation comes when the Carnot spiral looks like this figure 18a. Okay. The lower edge of the slit is shown by point B1 tilde, while the upper edge is shown by B2 tilde, and the resultant phasor is given by this straight line, okay, which we call B1 2 tilde. Now, this happens only for a particular width of the aperture. Now, in this particular case, if you widen up the aperture or shrink the aperture, in both the cases B1 will move from this position as well as B2 will move from this position. Okay. And if there is a shift in the position of B1 tilde and B2 tilde, then what will happen? This length of the phasor will increase now. Yeah, this is the minimum possible length of the phasor in this particular case. This is the minimum possible length of the phasor. Now, if suppose the B1 is here, it and then B2 would be here, the new position would be this one, which is larger than this earlier position. Similarly, if you shift B1 in this point, let us pick different color. Now, if you shift B1 here and B2 here, the new position would be given by this red line, which is again larger than this continuous red phasor. Therefore, if the point of observation is moved vertically either up or down, delta V slides either down or up the spiral, which is shown by this points. Yeah. Now, yet the chord increases in both cases, okay, which we understood. One, the new position of the chord would be given by either this dashed line or this continuous red line, okay. And therefore, the center of diffraction pattern must be a relative minimum in this particular width of single slit. The center would be minimum, which is given by this figure here, and this represents this blue continuous blue line, okay. And as we move away, play with the slit width, either it is decrease or increase, then what will happen? The phasor will increase, okay. Or what we can say is that as we move the point of observation up or down, then what will happen? That we will see an increase in the intensity, okay. Then let me reread it. As the slit widens, delta V becomes larger for a fixed R naught until a configuration like that in figure 18a, okay. Now, in this configuration, if the point of observation is moved vertically either up or down, delta V slides either down or up the spiral, yet the chord increases in both cases. So, that the center of diffraction pattern must be a relative minimum, okay, which is shown here. Now, in this position, as I said before, as soon as you move the chord up or down, the intensity should go up, and this you see here, the intensity is going up. Now, while going up, you see that it is again going through several maxima and minima if the chord winds up around B plus tilde or B minus tilde. Now, fringes now appear within the geometric shadow of the slit, unlike the Fraunhofer pattern in this particular case only. Okay. Now, this is all about single slit or thin slit. Now, we will start a new topic wherein we will see the fringe pattern due to semi infinite opaque screen. In this particular case, the edges Z2 and Y2 is extended till infinity and Y1 is extended till minus infinity. Yeah, in this direction the edge is extended till minus infinity, here till plus infinity, in this direction it is plus infinity, and here it is kept here at 0. Okay. But let us not say it is 0, let us say that it is not extended till minus infinity, it has some finite value, and therefore, Z2 and Y2 would be plus infinity, Y1 at minus infinity, as therefore, V2 and U2 would be equal to plus infinity and U1 would be minus infinity. And if this is the case, then from equation 60, which is given here in this green bracket, we will substitute for U1, substitute for U2 and V1, V2, and we know that these values are plus infinity and minus infinity. If you substitute here, then you will get that this value of this function is plus half, value of this function is again plus half, the value of this function is minus half, this is again minus half, and this function is equal to plus half, and this is again plus half, and f v1 is not known. Okay, this is something which is left. Okay, and this is also something which is left. Okay, these two functions would be left, and after all this substitution and bit simplification, we get equation number 69. Now, in this equation, suppose that point of observation is here at point number 3. Now, if observer is at a point number 3 in Fresnel domain, then it will see that the edge is directly in the field of view, here it is, okay, and you will see that origin is here at the edge. Therefore, the point V1 for point 3 would be equal to 0. Now, therefore, in this particular case point P is directly opposite to the edge and V 1 is 0. If V 1 is equal to 0, zeta 0 would be equal to f 0, which is equal to 0, and the value of the function or the value of equation 69 would be equal to I u by 4. Okay. Now, you see that had there been no aperture, we would have received irradiance which is equal to I u by 2, but now here we are getting I u by 4, and this is quite intuitive also, yeah, because we are covering half of the space with an screen. Okay. Now, since half of the wavefront is obstructed, the amplitude of the disturbance is halved and the irradiance drops to 1/4. Had there been no obstruction, we would have observed irradiance which is equal to I u. But since half of the wavefront is stopped or half of the wavefront is obstructed, the electric field reduced down by half, therefore, irradiance is reduced by 1/4, and which is we derived from our mathematical calculation, which says I p is equal to I u by 4. Okay. Now, on Carnot's spiral, if you want to represent this, then the point 3 is given here, which is which represents the case when the origin is rightly at the edge. Now, from point 3, if you want to calculate the irradiance, the upper edge is at infinity, yeah, because this is the edge and this the opening is extended till infinity, and infinity is represented by this point here, which is our b plus tilde. Therefore, the resultant phasor would be this, the phasor which start from point 3 and extending till point b plus tilde. Now, if we let us again go back into the figure. Now, if we go to a point 2, which is a bit down as compared to point 3, then if you place your new origin here, then in this particular case the edge, the coordinate of edge would be some non-zero positive number. Okay. Initially, when the origin was at edge, the coordinate of this edge was 0, but from point O, when the coordinate of this edge would be some positive number. Okay. And while the upper edge, which is at plus infinity, it will remain as it is. Okay. Therefore, the spiral or the chord which initially was starting from origin from point 3, it will now be shifted upward. Okay. The new position of the chord starts now from point P, and then the new vector will be from point 2 to point B plus tilde, because the other edge, the higher upper edge is till infinity. Yeah. Therefore, we will draw a vector which will start from point 2 and it will extend till point B plus tilde. Okay. Because our aperture is this. This is the open portion which is our aperture. It start from this line and extend till infinity. Okay. The infinity is always represented by B plus tilde, plus infinity. Okay. And the position of this aperture is changing as we are moving in the screen. Okay. Now, you see that for point 2, the new position of the phasor is this. Now, for point 1, which is even more down, more in the side origin, we will again see that new origin, from new origin the position of this edge is now again a positive number which is greater than its previous value. It means the chord will now move a bit more up, it would be now closer to B plus tilde point. Okay. Therefore, this new point, let us pick a different color. New point is represented by this phasor. Yeah, the new point is point 1 and the corresponding phasor is given by this blue line, okay, which is even smaller. Okay. This line is largest, smaller, smallest. It means as we move into the shadow region, as more down into the shadow region, the irradiance will drop off, it will drop slowly. Okay. Now, what would be the situation if we move upward? Okay, say we are observing now the pattern from point 4 as shown here in this figure. For point 4, the new position of the origin would be here, say it is point 03. For point 03, this edge, it would be negative number. Okay, V1 for O3 is negative, while the position of upper edge is still plus infinity, because infinity is infinity anyway. Okay. Therefore, for point 4, the chord will start from negative value and it will go till B plus tilde. Okay. And this is shown by point 4 here in this Carnot spiral plot. Now, from point 4, we draw this vector which extend till point B plus tilde, and this would be the phasor which will represent the resultant irradiance at point of observation 4. Okay. Now, if we move a bit more up at point 5, then this would be the position of new origin, say it is O4. For point O4, the coordinate of edge would be more negative number, while the coordinate of this upper edge again it is a plus infinity. Okay. While this lower edge is more negative, yeah, this distance is larger. Okay. In this case, the point 5 would be represented by this point on the Carnot spiral, and the resultant vector would be given by this dashed blue line. Okay. Therefore, what we saw is that in the positive direction or in the shadow region, if we move down, the phasor length is reducing. Okay. And while in the negative direction, this is our negative direction. Why we call it negative direction? Because we are moving our point of observation upward. Therefore, the edge is going into the negative direction. The coordinate of the lower edge, here in this case it is only one edge, because the other edge is anyway at infinity. Therefore, the edge coordinate of edge is going more into the negative direction as we move the point of observation upward. Okay. Now, you see that at point 4, the phasor is very long. Yeah, this was the length of the phasor, while for point 5 the phasor is this long, which is smaller than the phasor for point 4. Okay. And therefore, as we move more up, we will wind around the point B minus. Okay. This is our point B minus tilde. We will wind around this point. Okay. And while winding around this point, the phasor will go through several maximum or minimum. Okay. It will go through several extrema. Okay. Therefore, the fringes in upward direction, it will see several maxima and minima, while in the lower direction it will decay smoothly, and which is being plotted, which is plotted here in this figure number 21. You see, this is the position, this is in this axis we are plotting V, while in the vertical direction we are plotting relative irradiance I by IU. Okay. As long as V is positive, okay, these are the positive number. Okay. V positive means we are, the point of observation is in the shadow region, in this region. Okay. As long as we are in the shadow region, then only the coordinate of edge is positive. Okay. Then now, as long as we are in the shadow region, we see that the irradiance is dropping down smoothly. Okay. Now, if we are in the other side, if we are in the illuminated region, then V is negative, because if we are in here, if we are up, if we are above this edge, then the coordinate of edge will always be negative, and if the coordinate of edge is negative, in that case we saw that the length of phasor, which is plotted here, it goes through several maxima and minima. Therefore, we will see oscillations in irradiance, and these oscillations are shown here, and this is the position of point 4, the irradiance at point 4, this point represents the irradiance at point 5. Several maxima and minima would be observed here, okay, if V is negative. Okay. Now, at about V1 is equal to minus 1.5, which is this value, okay, the chord reaches a maximum and the irradiance is a maximum, which is shown here at 0.4, but this is which is shown here by 0.4 here in this Carnot spiral picture. Therefore, IP oscillates about IU, gradually diminishing in magnitude. Okay. This is IU, this horizontal line is IU value, and this oscillation is about this IU, and slowly the amplitude is decaying down. If you plot the envelope, you see the amplitude is slowly decaying down as you move more into up. Okay. And if we are in some up point which is very far from the edge, then it will ultimately lead to IU, which is the irradiance due to unobstructed source, okay, which is very much obvious also. If we are very far from the edge, it is almost unobstructed and we will see irradiance which is equal to IU. Yeah. Now, let us consider another case of diffraction, which is by a narrow obstacle. Okay. We have studied diffraction pattern due to slit, okay, narrow slit. But what will happen if we remove the slit with a wire? What I mean to say is that a slit is a opening in an aperture, but what will happen if we move to a case which is almost opposite, means the open portion in the slit is now replaced with a wire and the closed portion is replaced by opening. Okay. Here in the case of slit, the light is only allowed pass through this slit, but here in this case of wire, the light is allowed to pass through all spaces except for the places where wire is there. Now, this is the wire, this is the point of observation P, O is here. Okay. Now, you see that light is coming from this region and this region, but light is not coming from the places where wire exists. Okay. Now, the two regions, we have two regions where from we are receiving light, and they will give some diffraction pattern, and therefore, the corresponding chord which we can draw in Carnot's spiral would be given by these lines. Okay. This is the first spiral, okay, and this spiral is extending very close to B tilde minus, and the second spiral start from U2 and it is going to almost to B plus. Why? Because this is the wire which is inverse of a single slit. Yeah. Now, you see that the wire is obstructing the light which is coming from the source, and you can assume that the light which is received at the screen, it extend from this point, say this point is named as plus delta, and then it is extending till plus infinity, and this edge has say coordinate minus delta and it is extending till minus infinity. Now, this plus infinity point would be expressed by B plus tilde, minus infinity point would be expressed by B minus tilde, and this minus del and plus del, say these are represented by these 2 points U1 and U2. Okay. It means we have two chords now due to wire, narrow obstacle, and in between these two chords there are chord, or there is a region wherein there is no chord. The chord is non-existent between point U1 and U2 on Carnot spiral. Okay. Herein, I repeat, herein what we considered is that we envision a vertical wire, and the point of observation is a point which is directly opposite to the center of the wire, which is shown here in this figure. The origin is at the center of the wire and P is directly opposite to O. It means from point of observation P, we are seeing or the system is very much symmetric. Now, if you plot this case in Carnot spiral, there we get two chords. Why? Because there are two contributing regions extending from y1 till minus infinity and y2 till plus infinity. Okay. This values are nothing but these are y1 and y2. Okay, minus del and plus del. Since the wire is very thin, therefore I prefer to write del in their width, but these are the coordinates y1 and y2. Okay, they are extending from y1 to minus infinity and y2 to plus infinity, and therefore on the Carnot spiral these corresponds to two arc lengths from u1 to b minus tilde and from u2 to b plus tilde. Okay, these would be the two chords or two arc lengths which would represent the irradiance at point of observation P due to the narrow obstacle or narrow wire. Okay. Now, if we move ourselves laterally, then these spirals will slide up or down as per the rules which we discussed in last class as well as today. Okay. Now, since earlier we were having only one arc in the Carnot spiral, and then we know how to calculate the irradiance. There we have to just draw a phasor, and the length of that phasor depicts the irradiance at the point of observation P. But here we have two chords. Okay. Now, in this particular case, the situation would be quite different. Here for the lower chord, the resultant would be given by this phasor, which is b1 tilde u1. For upper chord, the resultant would be given by this phasor, which is u2 b plus tilde. Okay. And this is b minus tilde u1. Okay. Now, we have two phasors. What would be the resultant of the two? We will have to add them up vectorially. Okay. Now, as you can see from the figure, from the geometry, that they will never add up to 0. Okay. You will always see some finite value of irradiance at the point of observation P as long as it is symmetric. Okay. There are few points which we should note. The point number 1 says the amplitude of the disturbance at a point P on the plane of observation is the magnitude of vector sum of the two phasors b minus u1 and u2 b plus. Okay. If you add up these two phasors vectorially, this will give us the resultant irradiance at a point of observation P. Okay. As with the opaque disc, the symmetry is such that there will always be an illuminated region along the central axis. Okay. Here we will always get some light, some irradiance at the central axis, and this is also seen in the case where we covered the source with some opaque disc and observed irradiance along the axis, and there too the irradiance was not 0. Okay. And this can be seen from the spiral, since when P is on the central axis, b minus u1 arc is equal to u2 b plus, and their sum can never be 0, and therefore, we will always see some non-zero irradiance along an axis which is passing through point of observation P and starting at origin O. The arc length delta u represents the obscured region of the spiral. And what is delta u? Delta u is nothing but u2 minus u1. Okay. It represents the obscured region of the spiral, and which increases as the diameter of wire increases, which is very much obvious. If the wire is thin, then in the Carnot spiral these points are very close, but if wire is thick, for thick wire on the Carnot spiral these points would be very far. Okay. And therefore, it directly corresponds to the obscured region of the spiral. Okay. With this, let us move to new topic, which is Babinet principle. Now, the Babinet principle says that two diffracting screens are said to be complementary when the transparent region on one exactly correspond to the opaque region on the other and vice versa. Okay. Now, in this Babinet principle, let us define what complementary screens are. Now, two diffracting screens are said to be complementary when the transparent region on one exactly correspond to opaque region on the other and vice versa. Okay. And the best example would be the example of seeing this thin slit and thin wire. Now, these two screens are said to be complementary, because if you place this thin wire on top of the this single slit, then this wire will cover up the slit and we will have a completely opaque screen. Okay. Now, therefore, these two screens are said to be complementary. These two screens which are sigma 1, sigma 2. Similarly, say we have a circular aperture and circular disc. Now, the circular aperture has this opening and circular disc has this opening, it is extending till infinity. These two screens will also be said to be complementary. Okay, why? Because if you take this disc and put it on this circular aperture, then it will cover up the aperture. Okay, and you will have a opaque screen till infinity. Okay, then any such screens are said to be complementary. Now, let us assume that E1 and E2 be the scalar optical disturbances which are received at point of observation P when either complementary screen sigma 1 and sigma 2 respectively is placed. Okay. Now, this statement says that if we put a, say for example, circular aperture and then observe it diffraction pattern, then say it is E1, and if we put a circular disc and then observe the pattern on the point of observation P, then the corresponding field is E2, and if these E1 and E2 are the field due to this complementary screen, then the total contribution from each aperture is determined by integrating over the area bounded by the aperture. Okay. And if both aperture are present simultaneously, then there are no opaque region at all. Okay. This can be understood as follows. Now, suppose this is a circular aperture wherein this portion is opaque. Now, suppose this is circular disc where this portion is opaque. Now, if both the apertures simultaneously, then it will lead to a case where everything is open, then we will get no opaque region. Okay, because this disc stops the light which falls on the area of the disc, while this circular aperture stops the light which falls anywhere except for this opening. Okay, and the shaded region represents the opaque portion. Okay. Now, if we overlap, if we put these two apertures simultaneously, then there would not be any opaque region, it would be completely free. Okay. The light will come unobstructed. Now, with this we can write that E1 which is contribution from one aperture and E2 which is contribution from the complementary aperture, then these two fields would be equal to EU, which is the field due to unobstructed source. Okay. I repeat, suppose we have a circular aperture. In circular aperture, we have light can pass through this aperture, while if light falls on the other portion of the screen, it will be stopped. And similarly, suppose we have a circular disc and on this light falls, then it will not pass through, while if it falls at anywhere else, then it will be allowed to pass. Now, if we overlap these two screens, then the portions which initially was obscured, it would be open. Yeah. Now, say we have a disc screen, if it is overlaid with the circular aperture screen, then what will happen? The whole aperture would be open now. Okay. There would be no opaque regions. Okay. Because the aperture by its definition, whenever we say circular aperture, Then circular apertures means we have a big screen and there is a hole, circular hole there in the screen, okay, and this hole means there is a circular aperture. Okay. Now, we have a disc. Now, the disc is a aperture wherein apart from the region which is covered by the disc, everything is open. Okay. Therefore, this is why these two screens are called complementary. Now, if you put these two screen all together at a single place, same place, then what will happen? Everything would be open, okay, because the aperture for the disc would be region which would be beyond the disc. Apart from the disc, everything is defined as aperture, everything which is open, which is allowing the light to pass through. Okay. While in the circular aperture, the aperture is this circle. Okay. Now, if the two screens are placed together, the circular aperture and the aperture in the case of disc would come together and it will form an unobstructed aperture, which is extending from minus infinity to plus infinity. In this case, the light will go through without facing any obstruction, and therefore, if we put the two complementary screen very close to each other or on top of each other, then we will see a field which would be equal to the field from unobstructed source, and this is the statement of Babinet principle. This is what Babinet said. Okay. The principle implies that when E naught is equal to 0, when at the source when there is an unobstructed source, then E1 must be equal to minus E2, or when EU is equal to 0, then E1 would be equal to minus E2. It means these disturbances are precisely equal in magnitude and 180 out of phase. The disturbance due to one aperture would be equal in magnitude, but would be out of phase by 180 degree if they are produced by complementary screens. Now, this is exemplified by the slit and narrow obstacle as well as by circular hole and the disc. Okay. This is what we studied earlier in our last classes, okay, where we saw that the pattern produced by single slit is almost equal to the pattern produced by narrow wire. Similarly, the pattern produced by circular aperture is almost equal to the pattern produced by disc, but this statement is only true if we are in the Fraunhofer region. Okay. Now, let us see what does these mean on Carnot spiral plot. Okay. In Carnot spiral, we see that the point, if we join point B minus tilde and B plus tilde, you get this phasor, and this phasor represents irradiance due to an unobstructed source. Now, and this points which are B1 tilde and B2 tilde, they are the points due to some aperture. Now, say one aperture are the points which it tells that one would therefore observe exactly the same irradiance distribution with either sigma plus or sigma minus in place, where sigma plus and sigma minus are complementary screens. Okay. Note that only for the case of Fraunhofer diffraction, the complementary screens will generate equivalent irradiance distribution, while in the Fresnel regime the irradiance would not be exactly equal, or the Babinet principle would not be exactly true. It would be more accurate if we are in the Fraunhofer domain. Okay. Now, let us consider an example of single slit in narrow obstacle. We know that we have two phasors. Okay. Now, let us represent these two phasors in blue color. The first phasor, it here are represented by this blue color. Okay. It starts from point B1 tilde and reaches to point B minus tilde, while the second phasor starts from B2 tilde and it then goes till B plus tilde. Okay. Now, these two chords represents contribution from narrow obstacle, and the corresponding phasor would be represented by these two vectors, which starts from b minus tilde to b1 tilde and b2 to b plus tilde. These two vectors represents the corresponding phasors, okay, because in the narrow wire we see that there is two contribution, one from this left part of narrow obstacle and one from the right part of the narrow obstacle. From this part we get this chord and from this part we get this arc or this chord, okay, and from just by measuring this vector phasors which are extending from b minus tilde to b1 tilde and b2 tilde to b plus tilde, we can have an estimate of the resultant irradiance at the point of observation P. And to have the exact value of this radiance at point P, we will have vectorially add up these two phasors, and this region which is given by red arc, this represents a contribution from a thin slit, okay, which is a screen complementary to narrow obstacle, and the contribution from thin slit is plotted here by the red arc, okay. Therefore, the phasor arising from a narrow obstacle, which is given by this expression b minus b1 plus b2 b plus, added to that from a slit b2 b1, okay, b2 b1 represents a phasor due to narrow slit, okay. Now, when it is added to b2 b1, this yields an unobstructed phasor which is equal to b minus b plus, okay. When you add these three phasors, you get this line which starts from b minus tilde and it ends at b plus tilde. Yeah, let me repeat, from narrow obstacle we get two phasors which starts from b minus tilde and ends at b1 tilde, and second starts from b2 tilde and ends at b plus tilde. These two phasors are coming from narrow obstacle or narrow wire. When you add them up, you get the resultant phasor. The complementary screen, which is of narrow slit, it gives a phasor which is starts from b1 tilde and it ends at b2 tilde, which is given by this line. Now, if you add all three phasors, then you can say that this phasor, let us pick a different color for addition. Yeah. Now, let us add this vector with this vector and then finally add this vector. If you add all these three vectors, then what you get is this line which starts from at b minus tilde and it ends at b plus tilde, which is a phasor due to unobstructed source, which is what Babinet principle said. Yeah. If you add the contributions from two complementary screen, you will get a disturbance which is of unobstructed source. Now, this is all for today. Thank you for joining me. See you all in the next class.